Hello everyone, here is a tricky question based on Bohr's atomic model. What is the ratio of the shortest wavelength of Balmer series to the shortest wavelength of Lyman series of hydrogen atoms? As per Bohr's model, we know that energy for the nth stationary state is equal to minus Rydberg constant times z square divided by n square. Rydberg constant value is equal to 13.6 eV. Z is the atomic number. In the case of hydrogen atom, it is 1 because for hydrogen atom, atomic number is 1. And n is the value of the stationary state. So it's the energy difference that we calculate. That is delta E is equal to En2 minus En1, and that is equal to minus Rydberg constant times 1 by n2 square minus 1 by n1 square. n2 value should always be greater than n1. Now let's say we have several stationary states. When we say something as a Lyman series, if an electron that has gone to the excited state falls back to the ground state, then we call that as a Lyman series, for which n value is equal to 1, that is ground state. When we say something as a Balmer series, if an electron that has gone to the excited state falls back to the first excited state, then we say that that is a Balmer series, for which n value is equal to 2. But here they are asking shortest wavelength. This means that the n value has to be infinity, because energy and wavelength are inversely proportional as per this equation. Therefore, if we have to get the shortest wavelength, then the energy gap has to be the highest. So when it would be highest? Only when the n value is equal to infinity. But when the n value is infinity, when the electron is here, what would happen to the energy? Energy would become 0, because we are basically hitting the continuum. There won't be any interaction between the nucleus and the electron. So therefore, mathematically, when the n value is infinity, energy would become 0, which means shortest wavelength of the Lyman series, it is the energy of the state itself. That's what we need to understand. And when we say Balmer series, it is the energy of the state itself. So therefore, we can calculate it this way. Hc divided by lambda b to specify the Balmer series is equal to minus Rydberg constant times 1 by infinity square, which would be 0, minus 1 by n1 value, in this case is 2, because it is Balmer series. So 2 square is 4. So therefore, this would be equal to simply Rydberg constant divided by 4, because minus into minus will become plus, 1 by infinity square is 0. So that is one equation. And the other equation is Hc by lambda L, and that would be equal to minus Rydberg constant times 1 by infinity square once again, that is 0, minus 1 by n1 square. n1 value now is 1. So therefore 1 by 1 square, and that is equal to simply 1. So therefore this is equal to simply Rydberg constant. Let's keep this as equation 2. Now what they are asking? Ratio of the shortest wavelength of Balmer series to the shortest wavelength of Lyman series of hydrogen atom. Therefore, Hc divided by lambda b whole divided by Hc divided by lambda L is equal to what? And this would be equal to Rydberg constant divided by 4 whole divided by Rydberg constant, which we can write it as Rydberg constant divided by 4 times 1 by Rydberg constant, because this is basically Rydberg constant divided by 1. So we can write it this way. Common terms we can cancel. So this means 1 by lambda b divided by 1 by lambda L is equal to 1 by 4, which we can write it as 1 by lambda b times lambda L divided by 1, and that is equal to 1 by 4. So basically lambda L divided by lambda b is equal to 1 by 4. But that is not what they are asking. The reverse of it. The reverse of it is lambda b divided by lambda L we need to find out. So therefore that is equal to 4 by 1. So which means 4 is to 1. That is the correct answer. Therefore option 1 is correct.